Hello everyone. I want to start by apologizing about the quality of the two recordings of the first two lectures. I think the quality is a bit better this time, and I'll keep trying to find a way to get a better quality for these recordings. Okay, so in this lecture I want to cover section 2.1 from the book. And this section is about systems of linear equations and matrices. So let's start by talking about linear systems. So a system of linear equations also called linear system is given by one or more equations in one or more linear equations. Let me say better. In one or more variables. Okay, so a linear system is a bunch of linear equations, and these linear equations can have more than one variable. Okay, so what do I mean by linear? Linear means that all the variables are only multiplied by numbers. Okay, so we never multiply variables together. For example, x squared, xy, xyz are not allowed. Okay, and we usually write the constant term, so the term that doesn't contain variables, on the right hand side of the equations. So let me show you one example of a linear system. So this is a linear system given by two equations in two variables x, y. And variables are also called unknowns from the book. Okay, so we have two equations. The first one is x minus 2y is equal to 1, and the second one is 3x plus 2y is equal to 11. Okay, so we have two linear equations. You see that the variables are only multiplied by numbers, and the equations have two variables, x and y. What does it mean to solve a system? So to solve a system means finding values for the variables that solve all the equations at the same time. Okay, so we are looking for a value for some values of x and y for which the first equation is true and the second equation is true at the same time. Okay, so let's try to solve this linear system. And later in the next lecture, we are going to see a systematic way to solve these linear systems. But for the moment, let's just try to solve it by being clever. Essentially, we are not going to use a strategy to solve this. We are just guessing what we do at each step. Okay, so it should be clear that if we subtract from one equation a multiple of another equation, we get an equivalent system, and by equivalent I mean that we get a system with the same solutions for x and y. So in particular, we can subtract from the second equation this equation multiplied by 3. In such a way, we get rid of this 3x term. So this equation multiplied by 3 is 3x minus 6y equal to 3. So we copy the first one. And for the second one, we subtract the first one times 3. So 3x minus 3x gives us 0. And then we have 2y minus 3 times negative 2y. So plus 6y. So we get 8y is equal to 11 minus 3 times 1. So equal 8. Okay, now we have gotten rid of this term, the x term in the second equation. So we only have 8y equal 8 in the second equation. So y is clearly 1 because we just divide by 8 both sides. And if y is equal 1, we can solve the first equation for x, and we get x is equal 1 plus 2y, but y is equal to 1, so x is equal to 1 plus 2, which is 3. Okay, so the solution is x equal 3 and y equal 1. So let me copy the linear system at the top of the whiteboard. Yeah. And the solution is x equal 3 and y equal 1. Okay, so what's the geometrical meaning of what we have done? So there are two ways of seeing what it means geometrically to solve a linear system. Either we can concentrate on the rows of this system or on the column of these systems. So let's see the rows first. So the picture that we're going to get is called the row picture by the book. So whenever you see the book talking about row picture, what it means is the geometrical interpretation of the linear system by concentrating on the rows. Okay, so the rows are two equations in variables x and y. So as you already know, equations in two variables give lines in the plane. So each equation gives a line in the plane. And if we add, instead of two variables, three variables, x, y, z, we will get a plane in the three-dimensional space. But here we have only two variables, so it's a line in each equation gives us a line in the plane. And solving the system, is the same as computing the intersection of these two lines. So in this case we have two lines, but in general we can have more than two equations. And if we had three variables, then we would compute the intersection of planes in the three-dimensional space. Okay, so we have two lines and we are computing the intersection of these two lines. Let's draw these lines for this particular example. Okay, so this is the line of the first equation, x minus 2y is equal to 1, and this is the line of the second equation. Okay, and they intersect in a point, and the coordinates of the point are exactly the solution of the linear system. Okay, so this is the point with coordinates x equal 3, y equal. So if we concentrate on the rows, what we are doing is essentially computing the intersection of lines. Okay. Another way to get a geometrical interpretation of linear systems is by concentrating on columns. And this is called the column picture in the book. Okay, we can think of the variables as scalars and the coefficients of the two equations as column vectors. So we can rewrite this system as x, which is a scalar, times the column vector given by the coefficients in front of x, so 1 and 3, plus y, which is the second scalar, times the column vector given by the coefficients in front of y, so negative 2 and 2. And this is equal to the column vector given by the constant terms, so 1 and 11. Okay, so we have rewritten this linear system in this way, and notice that this is a linear combination of these two vectors that gives us this third vector. Okay, so finding the solution of this linear system, so finding x and y, so solve the system is the same as finding the scalars of a linear combination. So more precisely, we are looking for the scalars of the linear combination of the two vectors given by the coefficient in front of x and y that gives us the vector of the constant terms of the two equations. Okay, so solving a linear system under this interpretation is like finding the scalars of a linear combination. And so this gives a systematic way to find whether a vector is a linear combination of other two vectors, or in general if we have more variables or of any number of vectors. Okay. So whenever you wanna determine whether a vector is a linear combination of the other vectors, you set up a linear system that is interpreted in this way. And the solutions, if you find solutions, then the vector is a linear combination of the other vectors. If you don't find a solution, then it is not a linear combination. Okay. And finding your solution gives you also the linear combination. But what does it mean geometrically? Geometrically, it means that you write this vector, so an arrow in the plane, as a linear combination of these two arrows. So let me draw. Okay, so we have the plane, we have the arrow 1, 3, so this is 1, 3, we have the arrow negative 2, 2, and we have the arrow 1, 11. And basically, finding x and y means finding the scalars that you have to multiply these two vectors with, such that if you add the rescaled version of these two arrows, you get this vector. So the solution was x equal 3 and y equal 1. So we have to rescale this by 3. So this picture is going to be a bit problematic, but think of this arrow as this arrow rescaled by a factor of 3, and if we rescale this arrow by a factor of 1, we get the arrow back, and then this vector is going to be the sum of this rescaled arrow and this rescaled arrow. Okay, so we are looking for the right coefficients such that the rescaling of these two arrows, if we take the sum of the rescaling of these two arrows, we get the third arrow. Okay, so this is the geometrical interpretation of finding a linear combination, of showing that a vector is a linear combination of other two vectors, which is the same as the geometrical interpretation of solving a linear system. You can see a better picture in the book. It's figure 2.2 at page 33. So page 33. Okay, so this is it for the geometrical interpretation of linear systems. Let's now write the linear systems in a different way using matrices. So let me first talk about matrices for a bit. So this is one of the fundamental concepts that we are going to work with in this course. So what's a matrix? A matrix is just a two-dimensional. A matrix is a two-dimensional array of numbers. So they are numbers that are arranged as a rectangle. And these numbers are called the entries or components of the matrix. Okay, so the numbers in the array are the entries or the components of the matrix. And in general, when we want to refer to a particular entry given the row and the column, we use this notation. Okay, so we denote matrices with square brackets, and we denote the entries of the matrix by the letter A with two subscripts. The first subscript, so if we have A, I, J, I is the row and J is the column. Okay, for example, A23 will be the entry in the second row and in the third column. And if a matrix has m rows and n columns, so if a matrix has m rows and n columns, we say that it is a m by n matrix. Okay, so whenever we say m times n matrix, it's a matrix that has m rows and n columns. In particular, if a matrix has the same, so if a matrix has the same number of rows and columns, we call it a square matrix. Because it's exactly a square of real numbers. And in particular, if a square matrix has n rows and n columns, we say that it's a square matrix of order n. So since it's a square and it has n columns and n rows, it's going to be a matrix with n square entries. Okay, one important operation is that you can multiply matrices and vectors and column vectors. So we can multiply a m by n matrix with any n-dimensional column vector. So by n-dimensional column vector, I mean a column vector with n components. Okay, so you can multiply a matrix with a column vector that has the same number of components as the number of the columns of the matrix. For example, let's take this matrix 2, 3, 4, 1, 0, negative 1, and multiply it by this column vector. So since this matrix has 3 columns, the column vector needs 3 components. And we can multiply the two in this way. We take each row of the matrix and we multiply each component of the row with each component of the column vector, and then we add all of these products. Okay? So we have 2 times 2 plus 3 times 1 plus 4 times negative 2, and this is the first component of the resulting vector that is obtained by multiplying the first row and the column vector. The second component of the column vector is going to be the second row times the vector. So 1 times 2 plus 0 times 1 plus negative 1 times negative 2. Okay, so what we get is 4 plus 3 plus negative 8, which is negative 1, and 2 plus 0 plus 2, which is 4. Okay, so we get m dimensional vector, because the vector that you get has the same number of rows as the number of components equal to the number of rows of the matrix you started with. Okay. So what you get is a m-dimensional column vector. Okay. You multiply an m by n matrix with an n dimensional column vector, and what you get is an m-dimensional column vector. So there's another way to think about the multiplication of matrices and vectors in terms of dot products. So let's see, in the example before, we had this matrix 2, 3, 4, 1, 0, negative 1 times 2, 1, negative 2, and we got the vector negative 1 and 4. And it turns out that the first component of the resulting vector is going to be the dot product of the first row and the column vector. So instead of writing it as a row, we write it as a column vector. And if we take the dot product of that row with the vector, it turns out that we get exactly negative 1. If you do this product, you're going to get negative. If you do this dot product, you're going to get negative 1, because remember that the dot product is a number. And if we do the dot product of the first row, of the second row, as a column vector, 1, 0, negative 1, dot the vector 1, 2, 1, negative 2, what we get is 4. Okay, so this is another way of thinking about products of matrices and vectors. The components of the resulting vectors are the dot products of the rows of the matrices and the column vector. Okay. So there's a special matrix for each n. There is a special square matrix of order n, So it's an n by n square matrix that is called the identity matrix of order n, and it's denoted by I with subscript n. Sometimes when this n is clear, because for example we are working in R square or R3, we just don't write this number as a subscript. We just write I to denote the identity matrix. And this IN is the square matrix whose all entries are 0 except on the diagonal in which they are 1. So it's all the entries are 0 except on the main diagonal in which you have 1. Let's see the examples for. Let's see the identity matrices of order 2 and 3. So I2 is the square matrix of order 2, so it's a 2 by 2 matrix with 0 as everywhere except 1 on the diagonal. The identity matrix of order 3 is a 3 by 3 matrix with 0 everywhere except on the diagonal where we have 1. And it turns out that for every column vector of the dimension n, we have that if we multiply the identity matrix of order n, so let me call this vector v, if we multiply this matrix, this identity matrix of order n by the vector v, we get v back. Okay, so please check this and convince yourself that this is true. This is really easy to check. And note that whenever you multiply, so whenever you multiply a matrix A by a vector B, and we denote this product by AB, is the linear combination of the columns of A with scalars, so with the scalars of the linear combination given by the components of B. So this is another way of looking at the products of matrices and vectors. Let's see this on the example that we considered before. This product, 2, 3, 4, 1 times 2, 1, negative 2 is the same as doing the linear combination of the columns with these coefficients given by the components of the vector. So we have 2 times the first column, 2, 1, plus 1 times the second column, 3, 0, plus negative 2 times the third column, 4, negative 1. Okay, and it turns out that if you compute this linear combination, you get exactly negative 1 and 4, which is the result of multiplying this matrix by this vector. Okay, so whenever you multiply a matrix with a vector, what you get is a linear combination of the columns of the matrix, and the coefficients of the linear combination are given by these the components of this vector. Okay, so this is going to be important. The result of the multiplication is always a linear combination of the columns of the matrix. Okay, so let's now connect matrices with linear systems. So there's a way to write each linear system that we call matrix notation. So we write the linear system as a equation involving a matrix, a column vector, such that the products of the matrix and the column vector is going to give you another vector. Okay, and I'm denoting matrices by capital letters and vectors as usual. So how to obtain these A, X, and B? A is the matrix of coefficients of the left-hand sides of the equations. So a linear system is given by a bunch of equations, and A is obtained by taking the coefficients of the left-hand sides of the equations. X is a column vector of the variables that are in the equations, and B is the column vector of the constant terms. That are the right hand sides of the equations. Okay, so let's see how to write in matrix notation the original linear system that we considered at the beginning of this lecture. So we consider this linear system, x minus 2y is equal to 1, 3x plus 2y is equal to 11. Okay. Then the matrix A is given by the coefficients in front of the variables on the left-hand sides of the equations. So in the first column, we put the coefficients in front of the first variable, which is x. So here we have 1 and here we have 3. In the second column, we put the coefficients in front of the second variable, which are negative 2 and 2. Okay, so this is the matrix of the coefficient. Then we have a vector x of the variables, so x and y. So this is standard notation. Sorry, it's a bit confusing because we have both the variable x and the vector x, but this is standard notation. So remember that this x is different from this x, and I'm denoting this x as a vector by underlining it. Okay, so this is a vector and this is just a variable x. And then b is the vector of the constant coefficients, the constant terms on the right hand side of the equation, so 1 and 11. So in this particular case, these two column vectors have the same number of components, but in general they can have different number of components. Okay, because it depends on how many equations and how many variables you have in your linear system. Okay, and we can write this linear system in this way: a x equal b. So the matrix 1, negative 2, 3, and 2 times xy is equal to 1 and 11. And you immediately see that if you do this multiplication, matrix times vector, and the vector that you obtain, you set it equal to the vector on the right hand side, the equations that you are getting are exactly the equations of the linear system. So finding this vector xy such that this equation is true is the same as solving this linear system. Okay. So we have rewritten every linear system as an equation involving vectors and matrices, where a and b are given and x is what you need to find. Okay, this is going to be very important later, and let me finish this lecture by talking about the interpretation of linear systems with 3 variables. So if you have a linear system with 3 variables that we are going to call x, y, and z, then each equation, so if we concentrate on rows, so the row picture given by equations that define planes in the 3-dimensional space. Okay, because each equation in 3 variables is going to give you a plane in the 3-dimensional space. Okay, and I hope that this is clear. If this is not clear, we can talk about this during our meetings. But each equation with 2 variables is going to give you a line in the 2-dimensional plane, and each equation with 3 variables is going to give you a plane in the 3-dimensional space. It's always going to give you any equation is always going to give you a geometrical object that has 1 dimension less than the number of the variables. So if you have 2 variables, you're going to get a 1-dimensional object, so a line. If you have 3 variables, you're going to get a 2-dimensional object, so a plane in the 3-dimensional space. And each equation is going to give you one of those. And since we are solving possibly more than one equation, we are computing the intersection of these planes. Okay? So when we have 3 variables, we are just intersecting planes, if we think about rows. And see figure 2.3 at page 35 of the book for an example. I am not gonna draw planes because it's gonna be a mess, but you can see a nice picture on the book at page 35. So this is the row picture. What's the column picture of a linear system with 3 variables? So now we concentrate on columns to get the column picture. So now since we have 3 variables, we now have 3 column vectors. Okay. And we are basically looking at the solving the linear systems means that we are looking for the linear combinations for the scalars of the linear combination of these 3 vectors. Okay, the same that we did for 2 variables, but in that case we only had 2 vectors. In this case we have 3 variables, so we have 3 column vectors. And we are looking for the right linear combination that gives us as a linear combination of these 3 vectors the other vector that is the vector of the constant terms. Okay, but remember that in this case we have 3 vectors, but these 3 column vectors can be either can have many components depending on the number of equations that you have. So these 3 vectors can be in the plane, they can be 3 vectors in the 3-dimensional space, they can be 3 vectors in the 4-dimensional space, depending on how many equations you have. And if you want to see an example of this and you want to see a picture of a linear combination of 3 vectors, see pages 35 and 36 of the book, okay, for an example. But this is the geometrical interpretation of linear systems with 3 variables. And you can do the same with 4, 5, 6 variables and so on, but it's clearly harder to picture at some point. Okay, so this is it for this lecture. I prepared a list of practice problems that is at the end of the notes for this section. And in particular, if you're interested in advanced linear algebra, if you're interested in seeing linear algebra from a more abstract point of view, please do problem number 33 from the book. Is at page is from the problem set 2.1 at page 41 of the book. So that's a really important problem if you want to see a more abstract way of seeing these kind of things. Okay, so this is it for this lecture. Thank you for listening. Bye bye.